This is lecture 40 and we were discussing droplet combustion. We have discussed all equations and I also listed the variables that we need to solve for. So what I am presenting here now is a summary. So these are the equations that we have. Fuel species conservation equation in the inner region, then oxidizer species conservation equation in the outer region. You cannot have fuel species in the outer region. Okay. Remember what the inner region is between the droplet and the flame. Outer region is between the flame and the far field. Then energy balance at the droplet surface, that is at the liquid vapor interface that exists. Then energy balance at the flame sheet, and there is a liquid vapor phase equilibrium. So there are 5 equations and the unknowns are also listed at the top. These are m dot of fuel, so that's the burning rate, then radius of the flame temperature, Ts is the droplet surface temperature, and YFS is the fuel mass fraction at the droplet surface, that is at the liquid vapor interface. To get these 5, we can use these 5 equations. But we will not do the solution. Okay, we will not find the final expression. So this is just to give you an idea of how this is done. It's not difficult. We have all the equations, so this can be done. So we will not go into the solution modalities. You can read that chapter from turns and it will be more clear to you. And ultimately we are interested in these expressions. So there, once you solve, you will be able to get m dot f, for example. M dot f depends on the gas phase thermal conductivity. Kg, it depends on the radius Rs that we get for the droplet. Then gas phase Cp, and this is log of 1 plus something here, and this something is a B number. So this is the transfer number. So this is BOQ, BO comma Q. We wrote BQ for the problem of liquid droplet evaporation. Q actually reminds us that we are considering heat transfer effects and not considering actually mass transfer effects. So this is just heat transfer to the droplet. And this when we write BO comma Q, then it is for the combustion case. It's just a matter of notation. We wrote BQ for the droplet evaporation case. So this is this ratio, and you can see from here that QI, we have a term QI2L that actually we neglected. So even this can be 0. This is the one which is the heat transfer from the interface to the interior of the liquid, which we neglected anyway. If you want to make the model more sophisticated, we can include that and think of the droplet of having a temperature variation within, but we are not considering that. So this will also go. So this will only have delta Hc by nu plus Cpg into T infinity minus Ts, and it will have HFG here. So the droplet burning rate will increase if you have higher value of heat of combustion, for example, isn't it? For a given value of the enthalpy of vaporization for the fuel, if you consider the case when delta Hc is higher, okay, some HFG value, okay, 2 fuels of the same sort of HFG value, but one having a higher delta Hc will give you a higher value of B, and if you have a higher value of B, then the m dot f will also increase. So this is also a transfer number. This is a B number, or it's also called the transfer number. And apart from this, so we have got m dot f, which is this into log of 1 plus B, and there is also Rf equal to Rs into something here, which is log of 1 plus BOQ divided by log of nu plus 1 divided by nu. Nu is again that ratio, oxidizer to fuel mass ratio, based on stoichiometry. So we have this, and we have another expression for flame temperature. We have an expression for YFS. Okay. So these are actually the solutions, and again all these details are available in the book, so you can copy from there. RF was not clearly legible there. RF is RS times log of 1 plus BOQ divided by mu. In fact, RF by RS has a name. This is called a flame standoff ratio. So in a quasi-steady model of droplet combustion, this flame standoff ratio turns out to be a constant, but actually it's not. In a real droplet combustion model, it will have some variation with time. Basically, with time, the initial stage of droplet evaporation and the final stage of droplet consumption, there will be some variation of RF by RS. But this is called a flame standoff ratio. And what else do? We had a d square law for droplet evaporation, so we also have a d square law for droplet combustion. And you can derive that in similar lines with what we did for droplet evaporation. So droplet evaporation, we say ddt of the mass of droplet is equal to minus of m dot. So we can do that, and then mass of droplet we wrote in terms of liquid density and the volume of the droplet, which had the diameter of the droplet. So you can do that business, and then you can finally get this, where this is again a constant which pertains to droplet combustion, not droplet evaporation now. And this K is so this expression is also similar to what we got for droplet evaporation. Okay. But the B value is of course different. The expression for B is of course different in this case. And what about droplet lifetime? Droplet lifetime is this d naught squared by K. So this is d squared. We are doing d squared law, and the only difference now is that we are doing it for combustion. Remember that BOQ, as we saw a few minutes back, okay. So that essentially concludes our droplet combustion discussion. But we have to understand that we made a very simple model. In actual models, things are different, but it's not too bad either. See, where can we go wrong? We can go wrong in, for example, the quasi-steady approximation, or we can go wrong maybe at spherical symmetry, we can go wrong at the fact that properties are not constant. We took properties to be constant. Properties, things like that. Now, in the quasi-steady approximation, we just take a droplet of a fixed size and then drop the del T, the transient terms in the gas phase equations. And for most cases, people have verified experimentally that this will turn out to be all right. Okay. Spherical symmetry, of course, can be a problem, because spherical symmetry is actually only valid if there is not much effect of buoyancy or there is not much flow, right? And if you remember, we saw some short videos in the last class. So this is the one which IISc people had done, Indian Institute of Science, and then they had this droplet, and then their flames looked like this, isn't it? So these were normal gravity experiments, as I was telling you in the last class. So this had gravity in it. If you have gravity, then due to buoyancy effect, you will have flow like this and the flame shape will be like this. But you will notice that they were also doing d square law. Remember, on the left hand side of the video, you had this small box which was generating a curve. There was a red dot moving down. Okay, so it was generating some kind of a d square law. Okay? So this dot which was moving down. So it even for this case, some approximate d square law can be written. D square law, of course, will be better if you have d square law will be easier for us to understand if you, of course, have spherical symmetry, because our model was for spherical symmetry, and that will happen. That can happen if there is no convective flow, no convective flow, in the sense that, okay, you have this droplet, you are not blowing air or something from some direction. If you are not doing that, and also there is no gravity. So if you remove that, if there is no gravity, then you will tend to get a flame which is more like this. And we briefly saw that in that other video where we had heptane and toluene, okay, and they gave flames which were more or less symmetrical. And these were done, as I told you, these were done in free fall facilities. So there's like a long tower sort of a situation where you prepare an instrumented box in which you put the droplet, you place the droplet on fibers, and then you have electrodes, and then you ignite the droplet, and then you just drop the box. Of course, it's not as simple as this. So it's a long vertical tunnel you can think of, and as it falls, you will get 1 or 2 seconds of what is known as microgravity time. Micro, of course, means 10 to the power minus 6. So gravity is supposed to be there, but very small because it's free fall. If it is free fall, then gravity is kind of negligible. So it's of the order of, let's say, 10 to the power minus 6 g. There are other ways of getting this gravity. If you have an aircraft flying in a particular path, okay, it can also generate some time when there is a very small amount of gravity. Of course, you can have a microgravity time if you take your droplet combustion experiment on a space shuttle and do experiments there, or on the International Space Station, ISS. So people have actually done these experiments, not like I'm thinking of a possible experiments in my fantasy, not like that. These experiments actually have been done. So that's why people have done droplet combustion experiments on board space shuttle. Okay. And they have got flames like this. The one which I had shown you in the last class, that was in fact not on a space shuttle, but in a free fall experiment. So you could actually see spherically symmetric flame. Okay. But in general, that will not be there. In general, you will have flame which looks more like this, but there also you can write a d square law, and d square law is sort of d squared equal to d naught squared minus k into t, and that turned out to be linear. You saw that red dot moving, it was actually generating a straight line. So we learnt some aspects of droplet burning by writing equations assuming certain things, properties, quasi-steady approximation, spherical symmetry, constant pressure, and few other things. And this theory can be possibly modified by including flow. If you include flow, then the theory becomes more sophisticated, but in a preliminary course, we are actually not being able to do that. Okay, so that's why we stopped at that stage. Yeah, regarding properties. So the other thing is regarding properties. Now properties, this assumption is not bad. Actually, I told you something about properties for the droplet evaporation case. So we can have similar things for properties here also. So properties of course will vary, because the flame is at a high temperature, the droplet is at a lower temperature, the surroundings are also probably at a lower temperature. So, the properties will vary. If you say constant properties, it is not like you can force the properties to remain constant, it is out of question. You cannot do that, they are not under your control. But you can choose some representative property values which will give you reasonably accurate profiles and quantities like mass burning rate. So, in this case for droplet combustion, CPG is evaluated for the fuel at a temperature T bar, then thermal conductivity is like this. This is density of the liquid, and T bar is 0.5 times Ts plus T flame. So, this is the flame temperature. All right. So, we can get Ts, isn't it? Ts we can get as part of the solution. Actually, we can get YFS, and YFS and Ts are related through that Clausius-Clapeyron relation which I told you. So, you can calculate Ts, but once you get Ts, you still have to guess a flame temperature, because if you want to get a solution, you need properties, but if you need properties, you need a flame temperature, because the flame temperature is here. Okay. So, it is not straightforward in the sense that all right, you have to, even if you take Ts to be the boiling point temperature, still you have to guess the flame temperature. Once you do that, then you can get a T bar, and once you get the T bar, then you can calculate the properties. Then you can go back and calculate all these other things like m dot fuel and then BOQ and even the flame temperature, and then improve the calculations. So, it can be iterative in the approach. So, it will finally have to be iterative. But the point is that ultimately with these property approximations, you get reasonably accurate values. All right. So, that is about droplet combustion. As I told you, spray combustion is much more difficult. In spray combustion, you have multiple droplets coming out at different sizes, moving at different velocities, interacting with one another, competing with the oxygen with one another. So, it is not exactly the same thing. So, again, just to highlight why we did all this because droplet combustion is easier to study, but it still gives you some idea of how liquid fuel combustion takes place. Plus, it is not so bad an approximation if the spray is dilute, like if the droplets are far away from each other. Okay, it is not a very dense spray. So, if you are producing a spray near the nozzle, it can be dense, but far away from the nozzle, it can be somewhat dilute. So, in a dilute spray regime, isolated droplet combustion, it is not so bad. That's what that's how we actually justify what we have done, what we have studied here. Now, we have just about 2.5 lectures left, and we'll have to go to solid fuel combustion and at least cover some features of it. So, we know something about solid fuel combustion already, because we had some discussion at the initial stage in the introductory stage of the course. But then what are the solid fuels? So, you can think about some naturally occurring solid fuels and some other solid fuels which are not naturally occurring. So, among the naturally occurring solid fuels, you can have, let us say, wood and woody biomass, other biomass. Okay. You can have peat. Peat is actually something which is obtained from decaying woody plants, okay, in marshlands and watery bogs, things like that. Then lignite. Lignite is a lower form than coal, okay, poor quality actually. Then we can have bituminous coal, anthracite coal. These are some of the examples of solid fuels. These are some of the examples of actually naturally occurring solid fuels. So in biomass, you can have woody biomass, which and that can include woody biomass can, in fact, woody biomass includes wood, but it also can include soft woods and hard woods. Okay. You can also have other biomass, which can mean non-woody biomass. So these can be, just to give you some example, bagasse, straws, stalks, husks, etc. So if you don't know the meaning of all these things, you have to find these out. What is bagasse? It's actually, for example, if you have sugar cane, and if we extract the juice, what is left is bagasse. Okay, so it's a kind of a residue. So agricultural residues, for example, these are non-woody biomass. And so then there are straws, then stalks of plants, and then rice husk, for example. So these are also examples of non-woody biomass. Plus peat, I already told you. Then there's lignite, and then bituminous coal, anthracite coal. And I don't think I should go into details of this because you kind of know something about this. And even if you don't know, probably this need not be taught because you can read this up. I think you probably all know that anthracite coal has more carbon than bituminous coal, right? If we had more time, we would have actually spent more time on this, but right now probably that's not possible. Okay. So there is essentially, this is biomass, and then there is coal. You can say biomass and coal, right? And these are naturally occurring solid fuels. But there can be other kinds of solid fuels also. If somebody burns plastic, then that's not a nice thing to do, but that then becomes not a naturally occurring solid fuel, but some solid fuel. If you're burning medical waste, for example, in hospitals they have incinerators, they have medical waste coming in there, all right, all kinds of things, and then they incinerate that. So that the fuel is medical waste in that case. So there are lots of other examples like that. Typically, we have to appreciate the fact that the solid fuel combustion is really difficult to study. Okay, it is more difficult to study. Actually, if you think about it, gaseous fuel combustion is easier to study. Liquid fuel combustion is more difficult to study. Solid fuel combustion is even more difficult to study. Think about it from chemical composition point of view. When we talked about gaseous fuel combustion, it's like methane or butane or propane. But so these are properly defined fuels with chemical formula and things like that. And often the fuel and since you're talking about gaseous fuel, so it's the fuel and the oxidizer are in the same phase. So you don't have to do anything to prepare the fuel, right? But think about liquid fuel combustion, you have to do something to the liquid fuel, isn't it? If you try to burn liquid just as liquid, you can do that, but that's not an intelligent way of doing engineering, because if I take a can of liquid fuel and just try to burn it directly, it's not very good. What is the purpose that it will serve? If I have a tray in which I pour some liquid fuel and try to burn it, it will burn, but it will create a fire. Okay. But if you want to do controlled combustion, for example, an engine, So in diesel engine, you are making this spray, so you have to have this process of atomization, which prepares the spray. So atomization is a nice thing, where the liquid stream is broken into fine droplets, right? So giving you a spray, and I told you why we do this, because if you try to burn the liquid just as a stream, it's going to take a much longer time, and you want to break it into sprays and break it into tiny droplets, so that in the small time that you can give for combustion, those droplets can evaporate and burn, right? Because you are not getting a whole lot of time in an engine which is running at a high speed. So you can't do that. So you have to create fine droplets. So you're preparing the fuel. When you're doing liquid fuel combustion, you are preparing the fuel. Are liquid fuels chemically more complicated than the gaseous fuels? Yes, quite often they are, because they are, let's say heptane, toluene, these are actually, their chemistry is less understood. They're also heavier in the sense that they have more carbon atoms in them. That's one. Their chemistry is definitely less understood. If you look up Turns's book, there is discussion on methane chemistry. They're all reactions are actually listed. Reactions are listed with the pre-exponential factors, activation energies, the exponents on the concentrations of fuel and oxidizer. These are listed. So you go to chapter 5 of Turns's book, you will get the complete mechanism of methane combustion. Of course, even that mechanism probably has some flaws, and over a period of time you will see more reactions added. There are some values of the activation energy and the pre-exponential factor getting modified over time because of research. Okay. So methane combustion mechanism was less complicated few decades back, but now it is more complicated because people have found out more information. But it is still in a good shape, and then with that kind of mechanism you can predict things. Whereas for liquid fuel combustion, let's say for heptane, toluene, etc., the chemical mechanisms are not very certain. They're less certain than for methane. So less details are available. So that's one problem. Plus, a lot of commercial liquid fuels, they don't have unique formula, right? What is gasoline? What is diesel? Is there a particular formula? Chemical formula? No, because it's kind of many components in it, and you don't know which one is there. So if you buy gasoline from one petrol pump nearby and one petrol pump far away, if you go to UP, if you go to some other place, maybe it will change. Okay, depends on the source. And if you go outside India, if you go to other countries, the gasoline profile will also change. Okay, same applies to diesel also. So the fuel is more complicated, and the fuel has to be prepared. You have to break it down into sprays quite often, and then the droplet has to evaporate, come to the gas phase, then it can burn. So it's getting more complicated. If you go to solid fuels, it's even more complicated, because if you look at the list that I just now wrote down, wood, peat, lignite, bituminous coal, anthracite coal, what is the chemical formula? Do we know these well? So that's one question. Of course, there's no single chemical formula which can adequately describe this. Plus, if you think about wood, it's very easy to see that, as I said, there is soft wood, hard wood, there are different kinds of trees. And the physical and chemical structure is again different from one place to another. The kind of moisture, the amount of moisture that it will contain, the physical structure is also different, because the fibers in wood, fibers orientations can vary, right? So it's a complex thing which is difficult to describe. We spent more time on gaseous fuel combustion because it's easier to study. That's one. And secondly, we try to, if you get gaseous fuel, if we have plenty of gas, then it's actually a good thing for the country, and then we can burn that and all that. Because it's more clean combustion. If you have liquid fuel, we saw that soot particles were coming out. Remember the last two videos? Heptane, toluene. Toluene, for example, produced a lot of soot, a lot of particulate matter. So if you get gas, it's good. Of course, liquids have higher energy densities, so liquids are also required. But it's a complicated situation. Liquid fuel combustion is more difficult to understand. Solid fuel combustion is even more difficult to understand because of the variation in fuel properties, because chemically we cannot describe it that well, and the fuel depends on the source. Which tree you are talking about, which coal mine you are talking about. It will vary from one place to another. So we have to ask ourselves, why is it that solid fuel combustion is difficult to study, and then these are some of the answers, as I told you. So how do you burn solid fuel? So one possibility is that, of course, if you have, let's say, a log of wood, you've cut it from a tree, and then if you try to burn it, it doesn't appear to be a very good idea, doesn't it? If you just try to burn it like this. How else can you burn this? Let's say we are talking about wood coming from a tree. Will you burn it like this, like just a log? Probably not. You can make it like small pieces, isn't it? So some pieces, maybe they may not be all of the same size and so same shape, but if you break it into smaller pieces, it will probably be better, isn't it? Again, we understand that this is going to be more difficult. Now somehow we think that this will be more difficult, this will be easier. So break it into smaller pieces. Maybe you can reduce the time that is required for combustion. And plus also it's easier. If you have a combustion chamber, like in a wood stove for example, you can have these chunks of wood fed into the combustion chamber of a stove, wood stove, and then it's easier to burn because you can't put a whole log in, so in any case you have to cut it and things like that. But will the combustion of a solid fuel also depend on the size and shape of the fuel? Okay, to answer that, let's try to remember, I think I probably told you this before, that there are stages in solid fuel combustion, right? So first, what does it do? If this has to burn or this has to burn, first what does it have to do? There has to be a process of drying. So it can have, the solid fuel can have some moisture in it, and then it dries, correct? So there is some source of ignition, some flame established, so the solid fuel dries off. What comes after that? Pyrolysis. So I think we mentioned that. So this is pyrolysis. Pyrolysis has another name which you might see somewhere, that is devolatilization, right? Devolatilization. Pyrolysis or devolatilization can take place. Now, volatile matter is what comes out of solid fuels when the moisture is mostly gone and its temperature is rising. Suppose there is a flame around it, so it will get heated, and then first the moisture will come out, then the solid fuel will break down. So this is the thermal breaking, and because of the breaking down, it will produce some gases, some volatile matter, which will come out from here, okay, or from here, whichever fuel you are talking about. Some volatile matter will come out. Now, what is volatile matter? These are coming out from the complex structure of the wood or the coal or whatever solid fuel you are talking about. They are not exactly the same chemical composition of the wood, but there are some broken down components. So there may be some hydrocarbons, there may be some methane, there can be some carbon monoxide. Okay, all these are coming out.
They also may be fuel.
Yeah, they will act as fuel, but they're not exactly the same composition as the original one. So they are obtained because of the pyrolysis process. Now, pyro means heat. Okay, I think it's a Greek word. So pyro means heat, and lysis means to break down. To break down. So for example, when you are doing an analysis, you are breaking down a situation and trying to understand different aspects of it. So lysis has to do with breaking down. So pyrolysis has to do with thermal breakdown of the chemical structure. So if you have a long chain molecule, that will break down, giving you a smaller hydrocarbons and various things. So this pyrolysis is also called devolatilization because the volatile matter goes out. So since it's going out, it's D. So devolatilization. Okay, so first we have drying, then we have devolatilization. Drying takes place at lower temperatures, okay, maybe 100 up to 150 degrees Celsius or something. Pyrolysis can take place to higher temperatures. It requires higher temperatures than 150. So 200, 250, it starts and then it goes on 300, 400, 500 degrees Celsius. You can have pyrolysis. So that is devolatilization. So you have this wood and then it has lost its moisture and then it's releasing volatile matter. The volatile matter can burn in a flame, and that volatile matter can burn, let's say, in a flame around that log. Yeah. And then what is happening to that wood? It has lost the moisture, it's losing volatile matter. Now it has got some carbon, maybe some minerals in it or things like that. Okay. And in all this process, you finally are left with actually char. So the char will also burn. So this is drying, pyrolysis, and then you will have, so this is stage 1, this is another stage 2, and then you will have char combustion, char burning. Char is mostly carbon. Okay. Char is mostly carbon. So drying, pyrolysis, and char combustion. Now the other thing that I was raising is that does the fuel shape or size matter? Okay. Does a log of wood burn the same way as a small wood particle or a small coal particle? A very small micron size particle. Are these the same thing? Now if you have this log of wood, then we can expect very significant temperature gradient from between the surface and the interior. Correct? So if there is, by some means you have started combustion, you have taken a source of ignition around here outside the log, then it's getting heated, the surface will be hot and the interior will be colder. We can expect that, right? So there will be temperature gradient. So we can expect that it will take a long time for the interior to lose the moisture, then get pyrolyzed, then get converted to char and then burn. Fine? But if you think about a particle which is micron size, let's say a very small coal particle, and we use this in pulverized coal combustion in power plants. Okay, and we take the coal and then we'll pulverize it. Pulverize meaning breaking it into again very small size particles. What is the particle size like? It's micron size. So it can be 100 micron, 150 micron, but it can be even lower. It can even go to 50 micron, let us say. The diameter of your hair is about 70 micron. Okay, so it's less than 100 micron. So it's something like that. So such a small size. If you have such a small size, we do not expect temperature gradient, major temperature gradients in that. Right? So we can say that in a micron size particle, the temperature of the center and the temperature of the surface, they are going to be somewhat same. Well, it's a good assumption to say that the particle at all points of time remain at a uniform temperature. That temperature will increase as combustion proceeds. Okay. So, but it's uniform. Uniform means spatially, like radially. If you take the radial coordinate, the temperature doesn't change with the radial position. So that's a good assumption that you make. So here, in the log case, you have drying, devolatilization, and char combustion taking place sequentially in different layers. Okay, so it will first, nothing will happen at the center, then it will dry, then after some time it will devolatilize, after some time it will go to char combustion. But no, okay, let me clarify this. We should, what I said is not exactly correct. I should say that here it is sequential. Okay, the processes are sequential. Here it is simultaneous. I think simultaneous. Let me explain this because I got the wrong word a minute back. What I mean is, since this is colder, this is at a higher temperature, you can have pyrolysis happening in this region and drying happening in this region. Okay. And little later you can have char combustion here, and you can have pyrolysis here, and still drying happening here. Or maybe still later it will have char combustion in most of the places, but pyrolysis from the central region. So these processes are simultaneous. Whereas for a micron size particle, it's actually sequential, because at all instants of time, the entire particle, and it's only a very tiny particle, micron size particle, it's uniformly at the same temperature. So the entire particle is first drying, the entire particle is then devolatilizing, the entire particle is then burning as char. Okay. So size actually matters. Now, why do we break it into small sizes? Again, same logic as what we used for breaking a liquid stream into a spray with small droplet sizes, because unless these are small, this combustion is going to take a lot of time. In fact, solid fuel combustion will be even slower, and char combustion is in fact very slow. Char combustion is really slow. Since char combustion is really slow, you have to break this into very small particles, and even then it takes a lot of time. Now, to explain this situation, I will just show you a schematic which will help you understand the practical configurations that are used for pulverized fuel combustion. So let's look at this. All right. This is big enough, or yeah, this is better probably. So these are different furnaces which are used in power plants. So if you have studied power plants and thermal power generation by solid fuel combustion, coal combustion, you probably are familiar with the shape. So this is the boiler, right? So this is the boiler, and this is this part which you see. You have coal and air coming in through injectors, injected into the combustion space, and then burning takes place, and the hot gases move into this. They move into typically the second pass of the boiler. Right? So these are various configurations. These are various configurations which are used in practical burners, and okay. So this is called part A is called horizontal configuration, horizontal burner configuration. Again, nothing much needs to be explained here. This is called opposed horizontal. This is opposed horizontal, and this is actually tangential firing. So I'll come to tangential firing little later. This is called an opposed inclined, because this is coming like this. Opposed inclined means it's coming from this side, but it's coming from the opposite wall also. What is coming? Air and coal through nozzles. So coming from this side, but they are both inclined. They are not both horizontal. They are both inclined. So that is part D. In E, you have a single U flame. Okay, single U flame. So it's the coal air is coming like this, and then coming down, and then it has to go up. So it creates a U. And then if you can also have a double U if you do the same thing from both opposing walls. So from here it goes like this, from here it goes like this, and they both come like this. So these are various kinds of designs. And tangential firing is actually most common, the one which you see here. All right. And this is kind of a cross-sectional view, and you can see here details of a corner-fired boiler with tangential injection. So there are burners which is sending coal and air from 4 corners of the boiler. How many burners, how many such injectors are there? It appears to be 4 here, but it can be many more. So this is a horizontal section. Think about sections like this above also. So there are multiple burners at different corners. Okay, and they are injecting coal and air. So the coal comes with the primary air, as you can see in the figure. Coal comes with the primary air, but there will be additional secondary air also. And you will notice that at the center of this diagram there is a circle drawn with a dashed. Circle drawn with a dash. Okay, what is that? This is here it's actually not showing a flame. Of course, the flame will look like a ball, okay? But it's an imaginary circle. It's an imaginary circle, and the burners which are sending this primary air and coal, they are actually firing at tangents to this circle. Okay, they're firing at tangents to this circle. They're sending this coal and air. So this circle is imaginary, that's why drawn with a dash. Okay, it's not a physical thing which you see there. But of course, as you said, it will create a flame ball, which will be like a big spherical thing, almost. All right, so this same thing is what we saw here. But of course, in this view, if you look at C, in this view you cannot see the 4 corners, of course, this is just a front view. So you can't appreciate the fact that it's like from 4 corners you have coal and air coming and hitting at an imaginary circle at tangents and then producing a flame ball. But here you can see the effect. This plot still shows you the effect. It shows you that because of this tangential firing that you were doing, you are creating a lot of turbulence and you are creating a vortical structure, a vortex sort of structure, okay, in the center of the burner. What does that do? It creates very good mixing for the coal and air particles, and it also lets the coal particles to move like this and mix and burn, thereby increasing the time. So this is something which is good to learn. So we'll have to close in a few minutes, but let me just clarify what we are trying to do. We are discussing solid fuel combustion. I told you why it's more difficult than liquid fuel combustion, and I have also told you that it's difficult because not just because of the chemistry is not very well known, but the fuel's composition is not very well known. There is wide variation of composition from one place to another. But I also told you that the combustion process depends on size, right, as we would have expected. I told you that if you take a big size of wood or big chunk of coal, then the processes can become simultaneous. Drying, pyrolysis and char combustion can become simultaneous, whereas if you have small particle, then these processes can become sequential. Okay, so we have understood that. Now, since we do not have that many lectures left, we are looking at the solid fuel combustion situation, which is of most important to us. So it's a very important situation where we are considering pulverized coal combustion in boilers, because this is important from power generation point of view. Of course, we could have taken other examples like wood stove combustion, but again we'll run out of time, so I thought I will choose this one. Now here what are we trying to do? We're trying to see what are the various configurations possible, and the most important configuration as of today is this tangential firing situation, right? Is there something else also possible? Yeah. Even this sort of burner is possible, but this is less used, where we use primary air plus coal through this nozzle and the secondary air with some swirl. Okay. The secondary air with some swirl. Swirl is this motion around the primary air nozzle. So this can also be used. Typically, the primary air is heated, so you will see a number like 75 degrees Celsius here. It's the primary air and coal comes out at a velocity of, let's say, 20-25 meters per second. And the secondary air is preheated to 300 degrees Celsius. It has got swirl vanes. It produces swirl. Swirl to again improve mixing. And primary air is about 20% of the combustion air. You will also notice that there is a light up burner. So there is a burner which is used with oil to give the initial ignition. It is to make things easier. So this nozzle burner which you just now saw, the last slide, is also called a flare or self-turbulating burner. So this is a swirl burner, and because it creates this rotation with the swirl, it creates a stabilized flame ball. All right, so the other point that I should mention is that if you look up Turns's book, it doesn't have these details. So this is from a book. Some of the information that I'm giving you is from a book called Combustion Engineering. By Borman and Ragland. But you can find this sort of information also in power plant technology books sometimes. Some of the power plant technology books have details on coal combustion burners. This is just the introductory part of it. And what we will like to do is to understand the combustion of one single coal particle in some detail in the next two lectures that we have. So the tangential one which we saw, again some details here. Here it's the you saw that the primary air there is a in tangential tilting burners, there we saw that there is primary air coming in and there is secondary air. The secondary air doesn't have a swirl. Okay. So in the two kinds of burners we talked about, the one which is a flare burner has a swirl in the secondary air. Okay, and it's not corner fired necessarily, but the tangential tilting burners are the most popular ones where you fire from corners and fire at tangents to that imaginary circle. So that's the most popular one. This is the one which we are talking about now in this particular slide that you see. So there's no swirl that you're giving in the flow, but then how are you improving the mixing? By doing this tangential firing, you are actually creating a flame ball with a vertical structure and very good mixing. So you'll notice here that a large scale vortex at the center of the boiler creates intense mixing. Then there are primary pipes at the corner. So there's a primary air with coal which is moving from the corners. There are 4 corners, and these can actually, see, I cannot show 4 at a time, so I'm showing 2 from 2 different corners. So they can be moved up and down. Okay, and what's the advantage of that? Because the flame ball which you are creating with these 4 corners, burners coming from the 4 corners, they can be shifted up or down. So that will help in stabilizing the flame better. It can help in shifting the high temperature zone depending on your heat transfer requirement. Okay, so the flame zone can be shifted. That's the important thing to remember here. What is the degree of movement? The degree of movement is between 10 and 30 degrees. And the last point is that the angle and the velocity of jets can be adjusted to optimize the fireball size and location in terms of heat release, because the location is where it's determining how much heat release is taking place and where. Okay. and it also there is an issue of ash production, ash getting deposited on the walls and things like that. So these can be controlled. So to have better control, you want to be able to change the angle in the burners and also change the velocities. So those options are available. Okay, before we close, just one point. So these particles, I mean, if you think about it, we have this sort of a situation, and again you are sending coal and air through various nozzles. Okay. Whichever kind of firing, if it may be just opposed firing, or it may be corner fired, it can be tangential firing, whatever. But you are sending these particles. Okay. So what are the questions? Questions is that why small particles? We know that. We know that these are small particles because we want to reduce the time that is required for combustion. Correct? That's obvious. But then you can ask this question: is that what is burning? And where? Easy to answer. Coal is burning inside the boiler. No, that's not a very good answer. Okay, because we know that coal may not burn exactly as coal, because we understand that coal loses moisture, then loses volatile matter, and then it becomes char. So when I'm saying what is burning, I'm also asking this question: is the volatile matter burning or is the char burning? Okay. And where? So if you try to think of a particle which is moving like this, and it will move in some complex fashion because there is a vertical structure. There's all this movement taking place like this. Very complex turbulent flow field, which I cannot show just using a schematic here. But it's moving a complex path. So let's say it's moving in some way. Okay. This is not representative, as I told you, but it's moving in such way. So as it moves, what happens to the coal particle? Yeah, so loses moisture. Primary air is typically preheated, so its primary air, if it is heated to 75 degrees Celsius, it has lost some part of the moisture, but may not have lost all moisture, isn't it? So when it's entering, if it is entering at 75, 80 degrees Celsius, it has lost some moisture, but we cannot rule out the possibility that it has got some more moisture. So it will lose some moisture, and it will release volatile matter as it moves along. So as the particle moves along the path, it's actually losing stuff, and maybe its size is also changing because of that. We don't know. Okay, we have to think about it. So it's losing. It has lost moisture. It's also losing volatile matter. Right? Is the volatile matter burning? Yes. Where? What's this question? Where? In the flame ball region, closer to the nozzles. So the volatile matter is burning. And as it moves further, when it has lost its volatile matter, it's still in the high temperature zone, and then what is left of that particle is actually some mineral matter in it, some small amount of hydrogen maybe, but mostly carbon. So this is char. Right? So the char will burn, and the mineral matter will get converted to ash. So there can be an issue of ash going and depositing somewhere. So that's a huge problem, especially for Indian coals. So the volatile matter combustion will be closer to the burners. It's an earlier stage. Char combustion will take place later. It's sequential, remember. Isn't it? It is sequential. Small particles are burning sequentially. Which process takes the maximum amount of time? Char combustion process. Okay, and that is the reason the boilers are so tall. Boilers are so tall because unless you give them the space, the char will not burn. Fine. So this is a concise summary of what actually happens, but we have to close now. We'll stop here, and in the next class we will try to think about a particle and try to write at least some simple equations to estimate what will be happening during drying stage, pyrolysis stage, and the char combustion stage. We will pay special attention to char combustion because that is a bottleneck. It takes a very long time. Okay. As I said, that is why the boilers are so tall. So we have to understand. In the next class, we will try to attempt and understand that. Okay. Thank you.